Welcome back to doing some Leetcode. Let's help you get your next job. So today we're going to do Leetcode number 78, subsets. The problem statement is as follows. Given an integer array nums of unique elements, return all possible subsets, also known as the power set. The solution set must not contain duplicate subsets. Return the solution in any order. Great. So if you are like me, you might have read this problem and immediately been like, wow, this is going to be so easy. I'm going to take one, then one, two, then one, three, then two, one, and whatever. And it's going to be easy. I'm going to return it. I'm going to get that job. But if you look further for more than like 1 second, you'll see that, okay, if you make every single subset, you're going to have like a big O of n cubed time complexity. There's no way you're getting that job if you do that. So what we're going to do is we're going to teach you the best way to do it. You're going to get a way better time complexity. Actually, I'll be honest, for this problem, the time complexity, it's kind of going to suck anyways. When you see a problem like this, where it's like basically generate a bunch of different types of sets, those are typically going to be backtracking problems. So for this problem, we're going to actually end up trying to solve this with optimal time complexity. And by optimal in this case, I do mean the best you can get for a problem like this. So let's see. Sorry, just had to start my timer. But basically, for this subsets problems, we're going to consider a little bit of combinatorics. So in combinatorics, there's a concept known as permutations. Permutations are basically the different ways you can build up a sequence given the elements in an existing sequence. For example, in nums, we have 1, 2, 3. Now, if we think about it this way, for every element of nums, to generate a set from it, I can either choose to take that element or leave it. So for example, if I took all the elements, let's say I take 1, then the next option I have is to take or leave 2. Then I have the option to take or leave 3. So if I took 1 and 2 and 3, the subset would be 1, 2, 3. If I left 1 and I took 2 and I left 3, the subset would be 2. And I can repeat all these different combinations to get all the different permutations, which will be equivalent to exactly what the power set of a possible integer array nums would be. So we're going to think of how we can generate the power set. So like I mentioned, we can take any given element, take it or leave it. What we're going to do is we're going to implement a bit of backtracking. So in backtracking, it's typical to have a working set, some set that you are basically going to have a recursive function that is going to write elements to a working set, and then an output set. The output set is going to be the list of all the possible combinations that your backtracking function was able to compute. So we're going to start off by writing that out. I'm going to have, let's say subset. This is going to be our working set. I'll just set it equal to a link, or excuse me, equal to a list. Then I'm going to have my output. This is going to contain all the possible subsets, also known as the power set. Now we're just going to define our backtracking function. I'll just call it backtrack. Now this function is going to take in our case, what do we have? Well, we're going through element by element, considering the element at every index. So all we really need to pass into our backtracking function is going to be the index. And what we're going to do here is inside of our backtracking function. Again, backtracking is usually recursive. We're going to have a base case. So what's our base case going to be? Well, our base case is going to be once we've computed and considered every single element in nums. And nums has a length equal to, in this case, 3. So in other words, once we have an index that is equal to the length of nums, and again, this is 0 index, so when it's equal to the length, it means we've ran through all the elements in nums, and thus we should have a possible subset. So what I'll do is I'll say if I is equal to the length of nums, then I'm going to take whatever I have in my subset and I'm going to append it to my output. So I'll say append to output subset, but not just subset. Indeed, we're going to do subset.copy, and that's because subset alone would be a reference to the list. And if you didn't do .copy, or you could use, array slicing in Python. If you didn't do .copy, you would be appending the reference to the list subset. And as you went through different recursive call stacks, subset would end up equaling something else down the line. So we want to make sure that we copy the output, or excuse me, copy the working set to the overall output. Great. And then, of course, you want to return so that you don't infinitely loop. Now, we had two options that I outlined at every single element. We either want to take that element or we want to leave it. So let's say we're going to take the element. So when we take the element, all we need to do is say subset dot append nums of I. Great. So this is appending that to our working set. And then we're going to call our backtracking function. And we're going to call it with an index greater than 1 so that we continue moving through the length of nums. Now, we're not done here. We can't just go ahead and say, I want to call backtrack again for the case that I don't take the element. I actually need to remove from my subset the element we just added. And this is to ensure that it's not going to be considered for further recursive calls to backtrack. So now we're going to say leave the element. We've restored subset to whatever it was when this call stack of backtrack was indeed called. So we'll say backtrack of I plus 1. Great. Cool. So this is actually going to be the entirety of the backtrack function. All that's left to do in the main function now is to just call it. So what we're going to do here is we're going to say backtrack. And of course, if you're given a list, you need to pass in the first index in the context of this problem. So we'll say backtrack of 0, and then we're just going to return the output list. Cool. So this is the approach we're going to take for this problem. Let's look at the problem statement. We have a length of 1, so we don't need to check if nums is going to be empty. It'll never be empty. The elements are going to be from -10 to 10. That shouldn't impact what we've written. And all the numbers of nums are unique. Great. That's necessary to have a power set the way they defined it there. Great. So let's run through our code. I recommend you do this every single time just to ensure you didn't make any logical or syntactical errors. Let's see. We have subset, output. We have our backtracking function that takes in an index. Our base case is going to be if we've reached the end of nums, at which point we'll copy what we have so far and append it to the output and return. Then we have two options. We'll either take the element or leave the element. I'll do subset.append the current element when I do take it, call backtrack with the index incremented by 1, and then pop it. And then when I leave the element, I'm just going to call backtrack with I plus 1 because I don't need to append anything to my working set because in this recursive call chain, it's not going to end up having that element in the subset. Great. So this is our function. This is going to be the way that I recommend you solve this problem if you do want to indeed get the job. Let's run through an example. So I'm going to do a shorter example. Let's just say 1 and 2. I know they're saying 1, 2, 3 here, but look, there's like a bunch of cases and nobody has time for that. So in this case, we have 1 and 2. We're going to call backtrack of I with 0. The first case is going to be if we have I is equal to length of nums. It's not, so it's 0, so it's not going to be equal to length of nums, which is 2. So we continue and we add to our subset, and I'll say subset is going to be equal to 1. And then we're going to call backtrack with I plus 1. So now we're calling backtrack here. It's still not going to trigger this if statement because it's not going to be 2, it's 1. So we're going to see, are we going to take this element? Well, yeah, we're going to take this element again. And then we'll say 2. And then we're going to call with I plus 1 one more time. And we're going to come back to our backtracking function. And we'll see, is I equal to the length of the nums? It is equal to the length of the nums now. So we take what we have here, and we're going to snapshot that and put that into our output. Great. Now let's recurse back out, and we are now at the case where we are going to consider leaving 2. So we're here. We're going to just increment I plus 1 because we've now popped 2 from it. We're going to increment an I plus 1 and call backtrack, and we're going to say, hey, we're again in this if statement. So we're going to snapshot what we have now and add that to the output. So that's 1. Wonderful. Now we're going to recurse back out, and we're going to be removing or popping 1 from the call stack for 0. And now we're going to move down to leave the element, and we're going to say backtrack of I plus 1. Now we go again, and we see, hey, we have the case where we have 1 is the index, and we want to take the element, so we're just going to add 2 here. Then we'll call backtrack of I plus 1. It is now equal to the length of nums, so we're going to snapshot this and add this here. And then we'll recurse back out, pop 2, and then we're going to leave the element this time because we're at the case where we're going to exclude 2, and we'll call backtrack of I. And in this case, there's nothing, but we still want to include that. So we'll put the empty set, and that's always included in the power set of any set. And then we are done. We finished our recursion, we recursed all the way back out, and all we need to do now is return output, and this is going to be output. So what do you notice about this? Well, the length of our list, nums, is going to be 2 in this case, because we said nums is going to be 1 and 2, right? So the length is equal to 2. How many elements do we have in the output? We have 1, 2, 3, 4. So how could you get from a length of 2 in the input an output of 4? You could do 2 times 2. You could also do 2 to the power of 2, which is the length of the list. And of course, this isn't really the best example because it's impossible to follow the intuition from there. But what I'm trying to get at is the size of the input, the output will be 2 to the n of whatever the size of the input is. And if you see here, we have 3 as the length of nums, and then we get 2 to the 3 to the third power, which is 9, as the output. Great. So that is going to be actually quite relevant when we're considering our time and space complexity, which we can do now. We've done our dry run. I verbally explained the code. We ran through the code, and now we're going to do the time and space complexity. So let's look at the time complexity of this problem. Well, what are we doing? We're calling our backtrack function recursively from within the scope of the function. Of course, that's what recursive means, in case you didn't know. But we are calling our backtrack function how many times? Well, we have 2 to the n different options that we're going to end up snapshotting and putting in our output. So we call it at least 2 to the n times, right? But that's not where our time complexity ends. Notice that we're not just grabbing the subset and putting it in the output, we're also copying it. And you can imagine in the case of the subset 1, 2, 3, where the input is 1, 2, 3, the copying operation is going to be equal to the entire length of the input. So this, in the worst case, is going to be a big O of n operation, and we're doing that 2 to the n times. So our overall time complexity is going to be big O of 2 to the n times n. Great. And now, what about our space complexity? Well, a lot of people don't like to consider the output when they're talking about space complexity, but I think it's worthwhile. Our output is going to be of size 2 to the n. So we can say our space complexity, if we're considering the output as part of the space complexity, is big O of 2 to the n, right? So it's going to be big O of 2 to the n. But if we're not considering our space complexity, or excuse me, our output in the space complexity, then the only extra space we're using is actually going to be our list subset, which we use to compute all of the subsets, the power set. And subset, again, as we just went over, when we're copying it, it's at its largest going to be n, where n is the length of the input list nums. So we could say, if we're not counting the output, that we have n, big O of n, space complexity. So that's our time and space complexity. We have a time complexity of n times 2 to the n, and a space complexity of big O of 2 to the n, or big O of n, depending on what you decide to consider in the space complexity. So that is what we have. I hope you enjoyed this video. If you have any questions, please feel free to leave them in the comments. I'm realizing now I didn't actually run this, so let me run this and show you that it works, just so you know that I'm telling you the truth, and that you can indeed go ahead and take advantage of the solution. And look at that, it's amazing. Great, so thanks for tuning in. If you have any more problems you want me to work on, let me know. And if you have any questions, leave them in the comments below. Make sure to like and subscribe, and I'll see you in the next video.